The two types of friction are clear to you, Sanya? Static and kinetic.
Yes, sir.
Okay. Now, for any surface or any pair of surfaces, any two materials in contact, typically the coefficient of static friction will either be greater than or it will be equal to the coefficient of kinetic friction. So typical example is the coefficient of kinetic friction might be 0.4 and the coefficient of static friction it might be 0.5. Okay. Or we might have a situation where coefficient of static friction is equal to the coefficient of kinetic friction equal to 0.4. But it will never be the case where kinetic friction has larger coefficient and static friction has smaller coefficient. So that happens basically because when two surfaces are slipping, they cannot grip each other as well as compared to when they are in at rest with respect to each other. So two surfaces which are at rest, they grip each other better compared to two surfaces which are slipping. So that is the reason why generally the coefficient of static friction is slightly greater than the coefficient of kinetic friction for two surfaces. Okay. So this is again just a factual matter. Okay, now let us understand with a numerical example. So we have this situation now. Now for this surface, it is given to us that the coefficient of static friction is equal to 0.25 and the coefficient of kinetic friction is 0.20. And the mass of the block is given to us as 10 kilograms. We're taking G as 10 meters per second square. Now on this, we start applying a horizontal external force. Initially, the block is at rest. So first of all, we want to find out the acceleration of the block and the friction acting on it. If the magnitude of this external force is equal to in each of these. Okay. Initially, remember the block is at rest. Second part, Okay, so this is a situation where we are applying a force continuously, but for a duration of 10 seconds, and then we stop applying the force. Okay, so we have to also understand that when we stop applying the force, by then the block has developed some momentum because of some acceleration that we are giving. But when we stop applying the force, the surface on which the block is slipping is a rough surface. So it's not going to have that momentum forever. Eventually, the block is going to slow down and come to a halt altogether, or come to rest altogether. So we have to find after how much time the block stops. Okay. So just try this question out. We will discuss it in a minute. Okay, yes, very good. So see, the first thing you have to do here is you have to understand how much is the limiting friction available, maximum static friction kitna available hai. So for that, you have to check out how much the normal reaction is. So normal reaction is not getting affected by the external force we are applying. So the normal reaction is equal to mg for all cases. So that's equal to 100 newtons. Okay. So that is telling me that the maximum friction, static friction available is equal to 25 newtons. So what that is telling me is that for external force less than equal to 25 newtons, there is no acceleration. There will be no acceleration and static friction will balance the external force. Okay. That is what this is showing, that this is what will happen up to an external force of 25 newtons. Yes, so that's correct. So that is why in this A part also my acceleration will be 0, static friction will be 10 newtons. B part also my acceleration will be 0, but the static friction would have increased to 22 newtons. C part also the acceleration will be 0. The static friction would have increased to 25 newtons. Okay. But D part, now acceleration will not be 0. Okay. Very good. So D part, the acceleration will become 1 meters per second square. That is correct. Now we can see for F external greater than maximum value. Okay. So 20 newtons of kinetic friction will act. So this is what will happen in this case. So you'll see that okay, so that is why the acceleration will be 1 meter per second square here, and a kinetic friction of 20 newtons will be acting on the block. Right. So hope this is clear to all of you.
Yes, sir.
Yes, sir.
Okay. Okay. So now you see you start the second part. क्या हो रहा है second part में from t equal to 0 only, from the time I am starting my stopwatch. Okay, I am applying a force of 30 newtons continuously, but for 10 seconds. So that means for 10 seconds I will have an acceleration of 1 meter per second square. So that makes the first part very easy. But now you have to think is second part mein kya hoga when I stop applying the force of this much 30 newtons. So there's no external force. At that point of time, you think how the free body diagram is looking, and therefore what should be the acceleration or deceleration. So the hint to you is that by the time you reach 10 seconds, the block is already in motion. So even though you withdraw the external force, it is slipping. So always remember that whenever there is slipping, there will be kinetic friction opposing the slipping. So even when I stop applying the 30 Newton force, because the block has already started slipping, so what is going to happen? Friction is going to act till it brings the block to rest. Okay, so can you tell me after how much time the block will stop? Anybody got the B and C part? Okay, so this is, let's say, at t equal to 0, u is 0, but we start applying the external force of 30 newtons. Okay. So immediately there is kinetic friction that acts of 20 newtons that we have seen earlier. So it has an acceleration of 1 meter per second square. So at some general time t, but t is less than 10 seconds, it's having this acceleration. So by now it will have a velocity of kt. So by the time we come to t equal to 10 seconds, the velocity has become 10 meters per second. But the moment 10 seconds occurs, what is happening? We are withdrawing the external force. Okay. So at this point of time, external force is removed, but the block is slipping. So kinetic friction continues to act. So at some time, so you can see it starts decelerating. So from t equal to 10 seconds onwards, okay, what happens is that the block is decelerating because of kinetic friction. It has a velocity in the forward direction. So friction opposes that. So this kinetic friction provides a deceleration. Yes, very good, Ruksal. Okay. So we can say that the acceleration, okay, for t greater than 0, the acceleration is minus of 2 meters per second or minus a prime meters. So ये यहाँ से decelerate करने लगता है. So at some time greater than 10 seconds, we can see that because of this acceleration, the velocity is now reducing. V would have become less than 10 meters per second. So like that, at some point of time, okay, at some point of time, we have to find out when the velocity becomes 0. So the block comes to rest. Okay. And at that point of time, what happens? Friction stops acting because there's no external force acting tangentially. So friction also stops acting. Okay. So how much time it will take? So at t equal to 10 seconds, V was, how much was it? 10 meters per second. Okay. So at some time, 10 plus delta t, let's see. Okay. How much the velocity will become? 10 minus 2 delta t, u minus at, that kind of relation. Okay. So this shows us that the velocity will become 0 at delta t equal to 5 seconds. So the total time will be 15 seconds. So at 15 seconds, the block will come to rest. So this is a question which combines your concepts of kinematics along with your concept of kinetic and static friction. And we can also visualize the whole thing nicely like this, that if we draw velocity versus time graph, so that will be behaving like this. Velocity in meters per second versus time in seconds. So this graph will show us very nicely the kinematics of the motion. कि पहले क्या हो रहा था? For the first 10 seconds, वो 1 meter per second square पे accelerate कर रहा था. And then for the next 5 seconds, 2 meters per second square per decelerate करता है. So that is why it takes lesser time to come to rest, because the magnitude of the deceleration is more, now it's minus 2 meters per second square, whereas the magnitude of the acceleration here was this much. So in 10 seconds, It reached a velocity of 10 meters per second, and then it came to rest by the time it is 15 seconds. Okay, so hope this is clear to all of you.
Yes, sir.
Okay, very good. Okay, now let's see more situations with friction involved. So now, for example, if we have a next situation like this, but this time I'm pulling the block with a force like this. So I have this situation. So the block is at rest initially. And this force is applied at an angle of theta. The coefficient of kinetic friction and static friction is given to us. So in this example, let's say mass is equal to 5 kg and we're taking g as 10 meters per second square. Now force of 20 newtons is applied at theta equal to 37 degrees to the horizontal. So first part, if the block is at rest for F equal to 20 newtons. What is the minimum possible value of coefficient of static friction? Okay, that's the first part of the question. Second part, if for F equal to 25 newtons at theta equal to 37 degrees, okay, the block starts slipping at E equal to 0.2 meters per second square, then find the coefficient of kinetic friction. So start with the free body diagram for the part 1. Okay. In that, just apply the condition that the net force should be 0 because the acceleration of the block is 0. So from this, you'll get the value of static friction. And then from that, you can get the value of coefficient of static friction because you know that maximum static friction is equal to this value. Limiting value of friction is this. So from this, you can get the possible values of the coefficient of static friction. Okay. So hope the question is clear, people.
Yes, sir.
Okay. So just try this out. Free body diagram, you start with that. Remember that cos 37 is 4 by 5 and sine 37 is 3 by 5. Values. Okay, Ruksar, that's good. That's correct. Okay, so see, the first thing you have to do is resolve the forces correctly in the first diagram. So in part 1, you see what all forces are acting. You have the external force, you have normal reaction, you have mg, and you have static friction, because we know the object is at rest. Okay, so okay, look, sir, I'll check the second value also. Yes, it's correct. Okay. So when you resolve this, you can see that this component is f cos theta, this component is f sin theta, and the acceleration of the block is 0. So net force must be 0. So f cos theta is being balanced by static friction, and the sum of normal reaction plus f sin theta is balancing mg. Okay. So from the second equation, you are getting normal reaction as mg minus f sin theta. So that is 100 newtons minus 20 into 3 by 5. So that is 85 newtons. Okay, that's your normal reaction. And from the first equation, we are getting static friction acting is 20.
Sir, mass is 5 kg.
Oh, mass is 5 kg. My mistake. Okay.
Sir.
So ये 50 minus 15 हो जाएगा, correct? So this is how much now? 35 newtons.
30.
It's correct now? 35?
Yes, sir.
Okay. And this is going to be how much? This is 20 newtons. Oh, sorry, this is 16 newtons. So static friction acting is 16 newtons.
Sir, 38 will come.
Which,
Yes, sir, 38 will of n.
normal reaction is
38.
12. So 38 newtons. Yeah. And this one is 16 newtons, right?
Yes, sir.
So from this now, see what information we have, that static friction is less than equal to mu m in general. The maximum possible value of static friction is, okay. So that means that if you reverse this relation, mu s is greater than equal to whatever value of static friction is acting divided by normal reaction. So coefficient of static friction can be greater than, but also can be equal to this value 16 by 38. So that means the minimum value possible of coefficient of static friction is 16 by 38, which is how much?
0.2.
Huh. Yeah. So it is about 0.42, no? Okay. So this is clear now. It can be
Yes,
greater than
sir.
this also, but minimum to it, otherwise the
Yes,
object
sir.
cannot be at rest. So now have you worked out the second part? Second part, when we are applying the force of how much? 25 newtons, I think, right? Yeah, 25 newtons, we are observing the acceleration of 0.2. So from that, we have to get the coefficient of kinetic friction. Okay, theta is same, mass is same. Okay, so you have the same type of free body diagram, only the friction is now kinetic friction because there is slipping occurring. So we'll change this to kinetic friction. So this to an acceleration. So we'll have F cos theta minus kinetic friction is mass into acceleration. And again, normal reaction plus F sine theta is equal to mg. Okay. And we know that kinetic friction is equal to coefficient of kinetic friction into normal reaction. So from equation 1, we can see that 25 into 4 by 5, that's F cos theta, minus kinetic friction is the mass 5 kg into the acceleration of 0.2. So this time kinetic friction will come out to be 20 minus 1. So 19 newtons. This is the amount of kinetic friction that is active.
Yes, sir.
And from equation 2, we can see normal reaction kitna aa raha hai? 50 minus
12.
50 minus 15 होगा ना इस बार because it's 25.
Yes, sir.
So 35 newtons this time, na, normal reaction. Okay. So now we connect the two things. So this equation, this is telling us what, that the kinetic friction from here is 19 newtons. So 19 newtons should be the unknown kinetic friction into normal reaction 35. So the coefficient of kinetic friction is becoming 19 by 35, whatever that value is.
Point 5.
0.54, no?
Yes, sir.
So here the data is not very consistent because you are getting a value of, so assume that, you know, the second problem I've changed the material of the surface because kinetic friction cannot have a coefficient larger than, you know, static friction. So assume I'm using a different block, you know, in the second case. So that's why the value of coefficient of friction is different. Its mass is still 5 kg, but the material is different. So anyway, hope this question is clear, people.
Yes, sir.
Okay. Okay.
Yes, sir.
Yeah. Ruk sir, you're clear now with the values?
Yes, sir.
Yeah. Yeah. Okay. Now let's move on to some more typical type of questions to do with friction. So one type of question you have to be good at solving is something where pulley systems is combined with friction. So constraint relations that we've learned in Newton's laws earlier, that along with the concept of friction now added to it. Suppose we have this kind of a situation. Now for this surface, only a single value of mu is given. That means the coefficient of static friction is equal to the coefficient of kinetic friction equal to mu. So given M1 is suppose 10 kgs and coefficient of friction is 0.4. So first part, we have to find the maximum possible value of M2's mass such that the system remains at rest. And what is the maximum mass M2 that we can attach so that the system remains at rest? That's the first thing. And secondly, we have to find out if M2 is also equal to 10 kgs, then find accelerations of each block. How much acceleration each of the blocks are having. Ruksha, check your answer again, beta. So first of all, you have to understand one thing, na, कि यहाँ पे on the M2's free body diagram, there is tension of 2T acting. Na? So if the system is in equilibrium, 2T is balancing the weight of M2. Okay. So in the first part, we are assuming the system is at rest. So this one's acceleration is also 0, this one's acceleration is also 0. Yes, that's correct. Good. Now the answer is correct, Ruksha. Okay. So the condition for rest is M2G is balanced by 2T. And over there, tension is balancing static friction. And normal reaction is equal to this weight. Okay. So static friction is less than equal to mu N1. Okay. So that means now from here you can see tension is less than equal to mu M1G. And then you substitute this here. So tension is M2G by 2 is less than equal to mu M1. So this tells you that M2 should be less than equal to 2 times mu M1. So that means M2 should not exceed 2 into 0.4 into 10. So M2 should not exceed 8 kgs. So maximum M2 is 8 kg for no slipping condition. So hope this is clear to all of you people.
Yes, sir.
Very good.
Yes,
Okay.
sir.
Great. Now work out the second part where obviously there will be acceleration because we have taken the mass to be 10 kg now. So from the first part we are understanding because the mass is more than 8 kg, so definitely there will be acceleration. But remember, when it comes to this system, the two blocks will not have the same magnitude of acceleration because there's a system of pulleys. So constraint relation is important. Okay, so now if there is acceleration, what is the relationship between this one's acceleration A1 and this one's acceleration A2? Somebody tell me A1 A2 में क्या ratio होगा?
One is
A1 is to A2. Yes, that's correct. Okay. You can see that if this block goes down by a distance of x, it will pull 2x amount of thread now. So this will have to move by a distance of 2x. So the ratio of the acceleration will be 2:1. Yes. Okay. So this becomes the first relation. Then we have m2g minus 2t is equal to m2a2. And we have T minus kinetic friction is equal to M1A1. Okay. Now this kinetic friction will be equal to mu N1, which is equal to mu M1G. So from this, we can take the kinetic friction is 0.4 into, so it is 40 newtons. And in this, let us take E2 is equal to A. So A1 will become 2A. So equation 2 becomes 100 minus 2t is equal to 10A. And equation 3 becomes T minus 40 is equal to 10 into 2. So now we can solve this. Multiply this equation by 2 and add. So 2t will cancel out. So 100 minus 80 will become 10 plus 40 t. So 20 newtons is equal to 50 A. So A is equal to 2 by 5 or 0.4 meters per second square. So the A1 will be equal to 0.8 meters per second square. And A2 will be equal to, so A1 is like this and A2 is vertically downwards. Just check my calculation, but I think this is what you should be getting. So the rest of the application of friction mostly has to do with the same thing of Newton's laws of motion, applying the free body diagram to a system, etc. like this. So just write the values here. M1 is equal to M2 is equal to 10 kg. Mu is equal to 0.4 and G is equal to 10 meters per second square.
Understood, sir.
Understood, no? Good. Okay. Okay, so now see those who are having backlog or miss some lectures of friction, this with this basic concept of friction, you will be able to understand the recorded sessions and from my lecture notes. In fact, you can even directly do the questions from my lecture notes. And if you are having any doubt in any of the questions, how they are solved, you can then refer to the recording and right? And of course, we'll do some questions in the next session that we have for friction. We'll do some advanced type of questions like 2-block problems and 3-block problems. But before that, I want you to practice out more examples from the recorded sessions or from HC Verma also. You can do questions from friction chapter. Okay. Now, in the remaining time today, I want to move on to some basics of work by energy so that those who missed that section can also start with their cover up of work by energy. Right, all right, people, is that okay with you?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So let's look at the basic fundamentals of work by energy first today. So now the first aspect in this chapter is a new quantity, a new fundamental definition for us called work done by a force. So work done by a force, how this is defined. Now in the simplest case, if the force that we are talking about, F, is constant. If a constant force, that means constant in both magnitude and direction, both in magnitude as well as direction. If this type of a force is acting on a particle, so if suppose a force like this continuously acts on a particle, it doesn't matter how the particle is moving, but throughout its motion, the particular force we are talking about neither changes magnitude nor changes direction. So in that case, we define the work done as something very simple. It is dot product of force and displacement. So the particle moves from here to here. Let's say this is the displacement vector. So the work done is just F dot x. It is the scalar product of force and displacement. So that means if this is our force vector and suppose this is our displacement vector, then during that displacement, the work done will become Fs cos theta. Okay. So this is the definition of work done by a constant force F through a displacement of S. And as you can see, work done is expressed in joules, where 1 joule is equal to 1 Newton meter. Okay. And you can see that work done is a scalar quantity. Work done can be negative if theta is greater than 90 degrees. Work done can be positive if theta is acute. And work done can also be 0 if theta is 90 degrees. So this is about work done by a constant force. Okay. But now the more complex and the more general definition is, what if the force is not constant? What if the force is continuously varying? So that we call like more general definition of work done by a force. So suppose we have a situation where force acting on a particle is making the particle move along some path like this. So this is the initial position of the particle, and from here it is going by this kind of path to some final position. Now, while it is moving, the force that is acting on it is continuously changing. So it might be changing in such a way that only direction is changing, or it might be changing in such a way that only magnitude is changing, or it might be changing like I'm showing in my diagram, that both direction and magnitude are changing. Okay. So in that case, we cannot define work done as F dot S. If we define work done as F dot S, this will not make sense, because what value of force will we take in the calculation? Because force is varying now. It's a variable force. So throughout the displacement, that is from here to here, my force is not constant. So while the net displacement is this vector from here to here, whatever the initial to final is, but my force is not constant throughout it. So I cannot substitute some value of force over here. So this definition goes out of the picture. Instead, what we do is, because it's a variable force, we take a very small fraction of the whole path. So during a small displacement, during what we call a differential displacement. Differential means very small. So during a differential displacement, ds, okay, if during that small time during which that displacement is happening, if the instantaneous value of force is F, okay, then for that small part of the path, for that differential displacement, then for that small path, the work done is F dot ds. Okay. This is the work done for the small displacement ds. So therefore, the net work done becomes the summation of the work done for each and every small part of the path, like this. So we're dividing the entire path into small differential displacements, which are all adding up to give us the net displacement. So this is summed up by integration, okay, over the entire path from whatever initial to final position. So that work done becomes integration of F dot ds from initial to final position. Okay. So this is the broader definition of work done. And by this definition, we say work done equals the path integration. It's the path integration of force over the path from whatever initial to final position. So this definition is clear, people?
Yes, sir.
Okay,
Yes,
so hopefully we
sir.
understood, why we have to use integration when the force is variable. Because if we use the formula F dot S, the formula does not make sense, because between that displacement S, the force is changing in between. So what value of F will substitute? Okay, so that's why the general definition becomes like this. Okay. So actually, the first definition that we saw for constant force, it is a special case of the general definition. In this, if we put the force constant, then it comes outside the integration. So it becomes F dot integration of ds, and integration of ds becomes nothing but total displacement. So that's why it becomes F dot s. So we can treat this only as the general definition. This is the definition that always works for any case. But if the force becomes constant, then it reduces to F dot s, because we can take the force outside the integration. Okay, so let's start with a couple of examples. So now let's take a situation which includes friction also, because we've just learned about friction. So we have a rough surface of angle of inclination, let's say 30 degrees, and it has a coefficient of friction that is 1 by root 3. Or let's make it 1 by 2 root 3. So 1 by root 3. Now we have a block of mass m, which is placed on this rough surface initially at rest. And from here, it displaces down like this, such that after some time, it reaches here with some speed v, and through a displacement of s. So given that the mass of the block is 2 kilograms and g is 10 meters per second square, first of all make an free body diagram, an FBD of the block, and calculate all the forces. And the next thing what we have to do is we have to calculate the work done by each force through a displacement of s is equal to 10 meters. So if it is displacing through 10 meters, okay, then find v at s equal to 10 meters and show that the net work done equals half mv square. That is the kinetic energy that the particle has or that the block has at this point of time. Okay. So just use this definition that here you will see the forces are constant. So we can use this directly that it is F dot S for constant force. But the more general definition is that it is integration of F dot ds. This is the general definition. So here we will not need the general definition. We can just reduce it to F dot S because all the forces acting on this block, you can see they will be constant forces. Okay, so have you got the magnitude of the forces?
Yes, sir.
So tell me how many forces are there first of all on the block?
3.
Very good. 3 forces. Weight, normal reaction and friction. ठीक है. और ये फ्रिक्शन किस टाइप का फ्रिक्शन होगा? काइनेटिक फ्रिक्शन होगा?
Yes, sir.
You can see. Okay, so weight is 20 newtons. So how much is the normal reaction? Right. Theta was 30 degrees.
10 root 3.
10 root 3 newtons, or approximately you can say 17.32 whatever. Okay. So 10 root 3 newtons is a normal reaction. And what about the kinetic friction?
5.
It will be mu n. So 1 by 2 root 3 into 10 root 3. So this is equal to 5 newtons. Okay. So these are the forces: mg of 20, normal reaction of 10 root 3, and kinetic friction of 5 newtons. So you can see definitely the block will accelerate because mg sine theta is greater than friction. So you can also see that along the inclined plane, mg sine theta minus kinetic friction will be equal to mass into acceleration. So 10 minus 5 will be equal to 2v. So it will have an acceleration of 2.5 meters per second.
Yes, sir.
Okay. So that will come in handy in the third part, where we want to find out the v and show that the kinetic energy is equal to the net work done. Okay. Now next thing, we have to find out the work done by each of the forces for a displacement of 10 meters. So you can see that our displacement vector is down the inclined plane, so it's like this, and it's of magnitude 10 meters. Okay. This angle should be theta equal to 30 degrees. So compared to the displacement vector, now our forces are like this. One of the force normal reaction is like this, one of the forces friction is like this, and one of the forces weight is like this. So mg is 20 newtons, which we already shown, where this angle is 30 degrees, so this angle is 60 degrees. Okay. So work done by mg, we'll have to take dot product of mg with displacement. So we can see that it will become mgs cos 60 degrees. Correct?
Yes, sir.
Or that's the same thing as mgs sine 30 degrees. Okay. So it will become 20 into 10 into half, or plus 100 joules. So gravity is doing positive work. The work done by normal reaction सबसे easy है.
Yes, sir. 0.
ये हो जाएगा है ना. Very good, because normal reaction is perpendicular to the displacement. And work done by friction is also easy. Become minus of mu mg cos theta into s, because kinetic friction is opposite. Theta equal to 180 degrees with respect to the displacement. So this is minus of 5 into 10. 5 with na? Okay. So minus 50 joules. So as usual, kinetic friction always dissipates energy. It does negative work because it acts against the slipping.
Yes, sir.
So out of our 3 forces, one is doing plus 100 joules work, one is doing 0, and the other is doing minus 50. So the net work done will become the algebraic sum of these 3 in the third part. So that algebraic sum will become 50 joules.
Yes, sir.
Yes, sir.
So you should be able to verify that the kinetic energy of the block will also be 50 joules, because the net work done is equal to the change in kinetic energy. That will come as a theorem later, we will see, but here itself you can verify that with the data in this question. So this work done is clear by each of them.
Yes, sir.
Yes, sir.
Now third part, have you checked by kinematics what you're getting Vs? The displacement is 10 meters, right? The acceleration we had seen in the first part was 2.5 meters per second square. 2.5, yeah. Okay. And the initial velocity is 0. So we can use the relation. So we will come out to be square root of 2 into A, which is 2.5 into S. So that is root 50 or 5 root 2 meters per second. That is the speed. So therefore the kinetic energy, half mv square, is 50 joules. Okay. So note that the net work done, which is the algebraic sum of the work done by each of the forces, so that is becoming the same. You can see that in this case the net work done is equal to the kinetic energy because the initial
Yes, sir.
was 0. So this is already giving us an intuitive idea that there is a relationship between work done and kinetic energy. And we'll see next
Sir,
at
this is work energy theorem.
yes, work kinetic energy theorem. Okay. Okay. Now next let's look at an example of the general definition of work done. Integration f dot ds. Now in this also, if we have a situation of, suppose the system is one dimensional system, so the force is also along x-axis and the displacement is also along x-axis. So then this dot product results in just f dx. Okay. So in a 1D system it becomes like this. So let's look at an example based on that. So a particle moves along the x-axis under the action of a single variable force of F is equal to 20 upon x square along the positive x-axis, where x is position in meters, okay, and F is force in newtons. Okay. So first of all, find the work done by this force for a displacement from x equal to 1 meter to x equal to 4 meters. Secondly, if the particle of mass, let's say 1 kg, is released from rest, we'll make the mass 10 kgs. Yeah, so the 10 kg particle is released from rest at x equal to 1 meter, then find its speed at x equal to, let's say, 16 meters. By the time it reaches 16 meters, how much is the speed of the particle? So just try out this question. So this will give us an idea of how to deal with work done by variable force. Of course, in the 1D situation here, we will also see the general 3D case later. No, looks like the work done will be positive. Okay, I'll show you why it's positive. So work done will calculate by the general formula F dot ds, but here that will become F dx because the force is also along x-axis and the displacement is also along x-axis. Okay. Now you replace the force with the formula 20 by x square and you go from the initial position of x equal to 1 to the final position of x equal to 4. Okay. So this is the work done in this case. Now remember, integration of dx upon x square is x to the power
Minus
minus
x
integrate. So minus 2 plus 1 upon minus 2 plus 1. So very important, don't forget the minus sign. It is minus 1 by x. Okay. So that's why integration of 20 dx by x square is 20 this. Okay, so it is minus 20 by x plus. So this becomes minus 20 by x. Now we have to put the limits x equal to 1 to x equal to 4. So our upper limit becomes minus 20 by 1. Our lower limit becomes minus 20 by 4. Okay. So this is how we calculate the. Oh, sorry, it's the other way around. The upper limit is by 4. And,
Yes, sir.
okay. So this becomes plus 15 joules. That will become the work done. Okay.
Yes, sir.
So 15 joules is the answer for the first part. Now similarly for the second part, you have to just use the relation that the work done will be equal to the change in kinetic energy. Because you can't use kinematics here. Why? Because it's a variable acceleration.
Yes, sir.
Second part, if you go by the kinematics method, you can still do that. That's not a problem. But you'll have to do integration. Acceleration is F by m. So the mass of the particle being 10 kg, you will see it is 20 by x square divided by 10. So 2 by x square is the acceleration. Okay. So whenever acceleration is a function of x in kinematics, what we do, we express the acceleration as v dv by dx and we integrate. So that thing is one option there. So if you want to use kinematics, you'll have to do that. So v dv by dx is equal to 2 by x square. So v dv is equal to 2 by x square dx. Now integrate. So x equal to 1 meter pe, the body started from rest. And at x equal to 16 meters, I want to calculate whatever the value of v is. So this side will become v square by 2 from 0 to v. This will become minus 2 by x from x equal to 1 to x equal to 16. So this will be v square by 2 is equal to minus 2 by 16 minus minus 2 by 1. So that is 2 minus 1 by 8. So we'll get v square by 2 is equal to 15 by 8 or v square is equal to 15 by 4. So we will get v as square root of 15 by 2 in meters per second. So that is one option using kinematics. The other option is you can also use work energy. So we go by work energy. You can see that work done by this force F will be the change in kinetic energy because it's a single force F acting. So integration of F dx will be equal to half mv square. So it's the same kind of calculation that you get. Okay. So this will become minus 1 by 16. So it is half into the mass, which was 10 kgs into v square. So doing this calculation will give you the same result. Same thing. So understood now. So there's a correlation between combining Newton's law and kinematics. That is F is equal to ma, and then integration of acceleration gives us velocity. And there is a correlation between that and directly using work energy theorem, that the net work done is equal to the change in kinetic energy. And that correlation is itself called the work kinetic energy theorem.
Yes, sir.
Okay, people. So hope this is clear.
Yes, sir.
Yes, sir.
So again,
Yes, sir.
yeah, beta.
Sir.
Okay. So with this, again, I hope that you can get started with the work energy questions. Those who have missed the work energy early part of the lectures, you can get started with the questions from my class notes as well as from H.C. Verma. And those who are like clear with the basics, then you can continue with the more advanced problems of work energy theorem towards the end of H.C. Verma's exercise or from the module. And we can continue with the doubts of those type of questions in the next lecture. Okay. So that's it for today's session, people. Wish you all the best and thanks for attending.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Okay, bye.
Bye, sir.
Bye. Bye. What happened? Okay. Bye.